I wanted my game to have a dynamic security spotlight tracking the player. Easy, right? Just put a spotlight and point it in the right direction. But I have to say that it doesn't look very impressive. I wanted the light to project an actual image, like a bat signal, a grating shadow, or a sniper's laser sight. But simply incorporating the texture on top of an existing one doesn't seem like the right way to go. Perhaps we need to stop thinking like a painter and start thinking like a movie theater projector. Instead of throwing the texture into the world, we have to look at every single pixel on the floor and ask, if this pixel looked back at the projector, what part of the image would it see? Let's see if we can reverse engineer this algorithm. Imagine how you want the final result to look like. From this point, try to retrace the location and the direction of the projector. The projector can be high up with a view vector that points down, creating a square-like projection, or it can be lower with a view vector which hits the floor at a sharp angle, creating a stretched-out trapezoid kind of projection. Of course, we don't have to guess these attributes because they will be provided by the user, who will configure them to meet the requirements of the scene. Let's jump for a second into the seat of the projector and see how things look from there. We can move the projector, we can change the view vector and even change the field of view angle. All these attributes directly influence the final image. So this is basically a second camera in the scene. In the standard rendering pipeline, we transform from local space to world space and then to view space. We project the view space coordinates to clip space and perform perspective division to get the coordinates in NDC space. The system automatically handles the transformation from NDC space to screen space, and these coordinates are used for rasterization. What if we could add a second set of coordinates to each vertex, which will be calculated from the point of view of the projector? If this sounds familiar, then yeah, this is exactly how shadow mapping works, but instead of generating a shadow map, we use the NDC coordinates as UV coordinates that can be used to sample from the texture we want to project. Before we continue, I'd like to say a big thank you to Jan, who recently joined the 3D Underground. If you too would like to support this channel, you can do that at patreon.com/OGLDev or by joining the YouTube channel as a member. Let's see how to modify the standard process in this case. The projector doesn't have a physical shape, so we don't need any object space matrix for it, and because it functions like a camera, we don't need a separate world space matrix. The view space matrix will directly place the projector in the scene and point it in the right direction. This will essentially create a projector space with the projector at the origin, looking along the positive or negative z-axis, depending on the coordinate system. Of course, we will also need a perspective projection matrix. Let's see if we have enough to implement it. I've set the projector high up and to the right. The target of the projector is the origin, and the up vector should be pointing straight up, unless you want the projection to tilt from side to side. From these, we create a view matrix. For the projection matrix, we set a field of view angle, and the aspect ratio is 1, so basically a square. What about the near and far z? I'll let future me worry about it. For now, just plug in some values. Now multiply the view matrix by the projection matrix, and that's our projector matrix. In the Vertex shader, we add a corresponding uniform matrix for this variable, as well as a vec4 for the new projected texture coordinates. The position of the vertex is multiplied by the world space matrix of the object that we are rendering, and then by the projector matrix. So this is basically the position of the vertex as if it was rendered from the point of view of the projector. In the Fragment shader, we have a corresponding input variable. What's next? We need to sample from the projected texture. But wait a second. After multiplying by the projector matrix, the coordinates are in clip space, which goes between negative and positive W. We said that for sampling, we want to use the NDC coordinates, which range from -1 to 1. So we can manually divide by W, or we can use texture proj instead of the regular texture function and pass in the full vec4 coordinate vector. This approach is better because it is optimized by the hardware, which performs perspective correct interpolation. This of course includes the division by W. Now let's see the results. Okay, something is obviously wrong. The texture is definitely being projected and we can kind of identify the root of the projection, but the texture is all over the place. Well, the first thing that comes to mind is the clipping. This is handled automatically for the regular position coordinates, but what about the projected coordinates? There's no clipping there. Let's try to check this theory by visualizing those projected coordinates as colors. This requires a couple of steps. First, we map the NDC range of -1 to 1 to 0 to 1. And then we use the internal function fract to get the fractional part of the result. If the theory is correct and the coordinates go beyond 1, it will make it easier to identify it. As you can see, we have a repeating pattern of the coordinates. One solution to this problem is to manually get rid of coordinates that are greater than 1. But there is actually a better way. We can change the wrapping mode of the projected texture to GL clamp to border instead of the usual GL repeat. This means that the system automatically returns the border color when the texture coordinates are less than 0 or greater than 1. The default border color is black, which works well for us in this case. The results look much better now, but we can only see one half of the trapezoid. Where's the other half? The problem is, again, the NDC coordinates. The range of -1 to 1 must be mapped to 0 to 1 before we use them for sampling. We saw a similar thing with color. There's actually a more elegant and performant solution than doing this mapping in the shader. We know that this mapping calls for multiplying by half and then adding a half. So we create a matrix which translates the vector by a half, and we use it as an input to the function that creates the scaling matrix. Also by a half. The way the GLM works when the vector is on the right side of this multiplication is that scaling is applied first and then translation, which is exactly what we need. Okay, things are looking much better now, except that the texture seems to be stretching to infinity. The problem this time is that we have nothing that takes care of clipping at the far Z. We will have to do this manually. We calculate the projected depth and sample the texture only if the result is less than or equal to 0. This means that we need to be careful about setting the far Z in the perspective projection matrix of the projector because it will determine how far the projected texture will go. One final fix that I want to add is to check that the Z component in clip space is greater than 0. In some extreme cases, it can solve a problem where the projection is mirrored behind the projector. Notice that we have to check Z in clip space and not in NDC space, because if both Z and W are negative, the result will be positive. And that's it for today. Thank you for watching, and I will see you next time.